So in Math A30, you probably learned that the differentiation and integration of a function of a real variable. So for example, I can give you a simple example of such function. So f of x equals x squared. So a function is basically a rule which assigns a number with another number, right? So suppose if I plug in x equals 5, so this function f of x equals x squared is supposed to spit out another number, which is 25, right? So in single variable calculus, we learned the derivative of f of x is 2x, right? We also learned how to integrate f of x from a to b, right? So this is the integral from a to b of x squared dx, right? So in this class, we are sort of like considering similar ideas, except that we replace this function from c to c, right? So this is a complex valued functions. So before we start the differentiation and the integration of such functions, I will start by introducing the complex numbers. So what is a complex number? Well, the major player of complex numbers is the number I. So what is I? So I is the number such that I squared equals -1. So you can think of I as square root of -1, right? So a complex number is of the form z equals x plus iy, where x is a real number and y is also a real number. Okay, so I can give you an example. So first example, z could be, let's write 5 plus 3i. So in this case, x equals 5 and y equals 3. And the second example, they could just be 7i, right? So this is the case where x equals 0 and y equals 7. And the third example, z could be 15.5, right? So this is the case where x equals 15.5 and y equals 0. Right, so these are the examples for complex numbers. So we have a name for x and y. So x is called the real part of z, denoted by RE of z, and y is called the imaginary part of z, denoted by IM of z. Right, so I'll just write everything into a summary. So x equals real part of z, and y is imaginary part of z. Right. And if x equals 0, then z only has the imaginary part. Then z is called purely imaginary. So if y equals 0, so that means the imaginary part of this complex number is 0, then this complex number is, in fact, a real number. So the real numbers is a special case of complex numbers. Okay, so this is just one complex number. So now we want to consider the collection of complex numbers, and this is called the complex plane. Okay, so what is the complex plane? So I will denote by C, so this letter C, the collection of all the complex numbers. So this is the set of all the complex numbers. Right, so this is basically the set of all the z, which equals x plus iy, where x is the real number and y is also a real number. Right, so how does this set look like? So, well, here's the claim. This set looks exactly like R2. So this is the xy plane. So why is this? So claim. So here it is. So the claim is C can be identified with R2. Why? Intuitively, this is because here we said z can be written as the real part plus I times the imaginary part. And both the real part and the imaginary part are real numbers. So this gives us an identification of this z equals x plus iy with R2. So identification is given by whenever you have x plus iy, you just write x comma y, which is a point in R2, just like you learned in B41 and B42. So Z is a member of the complex plane. Right, so how do they look like? So I will draw a picture of the XY plane. So the picture of complex numbers are exactly like the XY coordinate for R2. So this is the x-axis, so this is also called the real axis. And the y-axis is called the imaginary axis. Right. So suppose I have a complex number, say like 2 plus I. So the imaginary part is 1, and the real part is 2. Right, so this point, 2 plus I, is a complex number. So on the complex plane, which is basically the same as the xy plane, the R2, right? So this point, you can also think of this point as 2, 1 in the xy plane, or you can also think of this complex number as a vector in R2, right? So this is basically how you can visualize the complex numbers and the collection of complex numbers. Okay, so we will move on to operations on complex numbers. So this is analogous to operations on real numbers. For example, if you have 2 real numbers, you can add them, subtract them, multiply them, and divide them. So now we want to understand what happens if you want to add 2 complex numbers, right? So suppose I have the first complex number, Z1, which is x1 plus I, I y1, and the second number is Z2 equals x2 plus I y2, right? So I want to add Z1 and Z2. So this is equals x1 plus I y1 plus x2 plus I y2, right? So I just copy down what is Z1 and Z2. So how do I add them? So the way I add them is exactly to group the real part and imaginary part, right? So the real part consists of x1 plus x2, and the imaginary part is I y1 plus I y2, and I can factor out this number I, so this I times y1 plus y2, right? So this is basically the formula for adding 2 complex numbers. And how you add 2 complex numbers is to add the real part and imaginary part separately, right? So how do you multiply 2 complex numbers? Multiplication. So we have Z1 times Z2, and I just copy what is a Z1 and Z2. So Z1 is x1 plus I y1, and multiply with x2 plus I y2, right? So how do I multiply? Well, the way you multiply is exactly like what you do for real numbers. You just distribute, right? So let's first let x2 to multiply with x1 and I y1. So you get x1, x2 plus I y1, x2, and plus, and then use I y2 to distribute. So x1 I y2 plus I square y1 y2, right? So now I have 4 numbers and I'm adding them up. So I will group the real part and imaginary part. So the real part, so x1, x2 is definitely the real part. And we note that I square y1, y2 is also real part because I square equals -1. So this is minus y1, y2. The imaginary part is I y1, x2 plus x1, y2. And this is the formula for multiplying 2 complex numbers. Right, so you don't really need to memorize all the formulas, but the most important thing is to understand how you get them. So basically the procedure is not difficult, you just distribute. Okay, so what are the properties for these operations? Right, so first we have commutativity. So this is to say that Z1 plus Z2 is the same as Z2 plus Z1. So if you are adding 2 complex numbers, you can swap the order of Z1 and Z2, and the result is the same. Right? So why is this true? Well, you can go back to the formulas Z1 plus Z2 and calculate similarly what is Z2 plus Z1 and compare the left-hand side and right-hand side. So this is also the case for multiplication. So if you're multiplying Z1 with Z2, it's the same as multiplying Z2 with Z1. And as I said, so to check these formulas, So you just calculate the left-hand side and the right-hand side and compare to see that they're the same. Okay, so the second property is associativity, which says that if you're adding three complex numbers, so you can add the first two complex numbers and add the sum to the third one, or you can add the second and third one together first and add their sum to the first one. And this is also true for multiplication. When you're multiplying three complex numbers, you can multiply the first two and then use the product to multiply with the third, or you can multiply the second and the third first and use the product to multiply to the first one. And again, you can check these formulas by calculating the left-hand side and right-hand side and compare that they're the same. Right, the third property is distributive law. So when you have multiplication and addition together, you can distribute. So you have z1 multiplied with z2 plus z3. This is the same as z1 dot z2 plus z1 dot z3. Right. So if you know slightly more, these properties basically says that the complex numbers is a field. Right, so in your algebra class, you learned vector spaces over a field. So we know the real numbers is a field, the rational numbers is a field, and today we know that C is also a field. The complex numbers is also a field. Right, so the next topic is absolute values. So this is the similar idea to the absolute value of real numbers. So, for example, if you have -5, right? So what is the absolute value? The absolute value of -5 equals 5, right? How do we see this? Well, let's draw the real line. Right, so here is 0, here's 1, 2, 3, blah, blah, blah. And here I have -1, -2, -3, and maybe -5 is here. And dot, 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 right? So here is -5. And what is the absolute value? So the absolute value of -5 is 5, and this is nothing but the distance between -5 to 0, right? So 0 is the starting point, so this distance equals 5, right? For complex numbers, the absolute value is the same idea, right? So we had the example where we have 2 plus I, right? And here I have the origin, which is 0 and 0. And I can ask, what is the distance between 0 to this point 2 plus I in R2, right? So how do you do this? Well, what is this distance? Well, let's make the following observation. So if I draw a vertical line starting from this point to the real axis, so the horizontal distance is 2, the real part, and the vertical distance is 1, so this is the imaginary part, right? And we note that this is a right angle triangle, right? So the distance between 0 and 2 plus I equals the square root of 2 squared plus 1 squared. And this is square root of 5, right? And what is this distance? Well, this is exactly the absolute value of 2 plus I, right? So that is to say, more generally, if you want to find the absolute value of the complex number x plus iy, then this basically equals the square root of the real part square plus the imaginary part square. And this is square root of x squared plus y squared, right? Oops. And this is the formula. So the absolute value of a complex number is square root of x squared plus y squared. Right, so what is the property for absolute value? Well, this is called the triangle inequality. I'll first write this down. So if you have z1 and z2 as two complex numbers, you can add them together. So z1 plus z2 is another complex number. You can take the absolute value of this complex number z1 plus z2, and you can also take the absolute value of z1 and the absolute value of z2, right? So the triangle inequality says the absolute value of their sum is smaller than or equal to the sum of their absolute values, right? So why is this true? So I will draw you a picture. And before I draw you a picture, let's make the following observation. So the claim is that this absolute value is the same as the length of the vector in R2. So this absolute value is the same as the length of the vector, so real part of z and imaginary part of z, or you can write it as xy, so this is a vector in R2, where R2 is a vector space, right? So how do I do this? So if I have z1 here, this is a point on the complex plane, so you can also think of it as a vector, right, in R2, and I can have another vector, z2. So what is z1 plus z2? So z1 plus z2, you can write it as the formula we wrote down before, but on the picture, this is exactly the same as how you add two vectors. So you basically just parallel translate z2 to the place where the head of z1 and the tail of z2 coincide, right? So this is, and the vector z1 plus z2 is this one. So this is the point where z1 plus z2. So basically, here we have a triangle, right? And from the triangle, you can see that the length of the hypotenuse is smaller than, or length of one side is smaller than or equal to the sum of the other two sides. So this is true for the length of sides for any triangles, and this proves the triangle inequality. Okay, so next operation is called complex conjugate. Right? So z equals x plus iy. What is the complex conjugate? So complex conjugate, where we denote by z bar, and this is nothing but changing the imaginary part from y to minus y. So the complex conjugate of z is x minus iy. Okay, so how does it look on the picture? So here we have z equals x plus iy, and where is x minus iy? So the real part is still x, and the imaginary part is negative y. So it's the symmetric image of z about the real axis. So this is x minus iy. Okay, so what are the properties for complex conjugates? Well, you can check first that if you add z plus z bar, you basically get 2x, right? So I divide it by 2, and I should get x, and x is the real part of z, right? And similarly, I can get the imaginary part. So I first calculate what is z minus z bar, and this is 2iy, right? And I divide it by 2i. So I should get the imaginary part, which is y. And I also have the following. The absolute value of z squared equals z times z bar. So why is this? So x plus iy times x minus iy, and this is x squared minus I squared y squared. So this is x squared plus y squared, and this is exactly the absolute value squared, right? Because the absolute value is square root of x squared plus y squared, and we want to square this number. This is x squared plus y squared, and the left hand side equals the right hand side, and the formula is verified. And similarly, 1 over z equals z bar divided by absolute value of z squared, and this follows from 3. And also, provided z is not 0. Okay. We have seen that a complex number can be presented as the real part plus I times the imaginary part. There is another presentation of a complex number. This is very similar to the polar coordinate for R2. So this is called the polar form of non-zero complex numbers. Great. So if z is not 0, then z can be written as z equals r e I theta. Right, so r is a positive real number, and theta is any real number. Right, so this looks different from the expression where you have real part and imaginary part, right? So how are they related? Well, this is related by this formula. So what is ei theta? This equals cosine theta plus I times sine theta. So this formula is the key which connects the polar presentation to the usual imaginary and real part representation, right? So z equals r ei theta equals r cosine theta plus I times r sine theta, right? So this is the real part. X equals r cosine theta and y equals r sine theta, and this is exactly the polar coordinates for xy plane, right? Okay, and under this representation, under the polar form representation, what is the absolute value of z? Right, so we know the absolute value of z equals square root of x squared plus y squared, right? And x squared is r squared cosine square theta plus r squared sine square theta, and this is r squared times cosine square theta plus sine square theta, and oops, this is basically square root of r squared, which is r, right? So r is basically the absolute value of z. So let me just draw this picture again. And this is exactly what you learned from B41, B42 for polar coordinates. So here is x plus iy, or the point xy in R2, right? So what is r and theta on this picture? So if you draw a line, or you draw the vector xy in R2, so we showed r is the distance, or the radius, from 0 to x plus iy. And what is theta? So theta is basically this angle. So theta is the angle that the point, that this vector has with the axis. So the orientation is counterclockwise. So you just measure what is the angle between the x-axis and the vector xy in R2. Okay. So polar coordinates are very useful in many ways. So I will point out one useful thing. That is to say, when we multiply two complex numbers, if you write two complex numbers in the polar form, so R1, okay, so e I theta 1 and z2 equals R2 e I theta 2 for some r and theta, right? So if we multiply two complex numbers, z1 and z2, so R1 e I theta 1 times R2 e I theta 2, this equals R1, R2, this is exactly the same as how you multiply for real numbers. So e I theta 1 plus I theta 2, this is R1, R2, e I theta 1 plus theta 2. Right, from this formula, for multiplication, we can see that when you multiply the complex number z2 to z1, what it does is the modulus, like the absolute value of z1, gets scaled by the amount of absolute value of z2, which is R2. Right, and there's a scaling factor, and when you look at the angles of theta 1 gets rotated by the amount of the angle for z2, which is theta 2. Right, so the angle for the product equals theta 1 plus theta 2, and the modulus for the product equals R1 times R2. Right, so this basically lets us to see that multiplication for complex numbers corresponds to scaling and rotation. Right. So I would also like to recall an important concept, which is convergence in analysis. So you probably have learned this in A31 or B41, B42. So we say that a sequence of complex numbers Cn, where n is greater than or equal to 1. So what is this? This is basically you have a sequence of complex numbers, or you have a sequence of points in R2, like you learned in B41 and B42. Right. So you must have learned this in multivariable calculus. You have a sequence of complex numbers, z1, z2, and z3. This sequence is said to converge to another point w in the complex plane if the following is true. So you measure what is the distance between the nth number zn in the sequence and w, and you take the limit as n goes to infinity, right? So you measure the really large n, the distance between zn minus w. So if you make n larger and larger and larger, then the distance, the absolute value, will go to 0, right? So this is what we call convergence. And we can also write some notation, like the limit as n goes to infinity of zn equals w. Right. Right, so whenever I write this notation, I always mean that this is true. The distance between Zn and W as n goes to infinity equals 0. And I write the limit of Zn equals W, right? And this is exactly the same as what you learned in B41 and B42. This notion is the same as convergence in R2, right? So you can have a sequence of points in R2 which converges to another point in R2, and the definition is exactly the same. You also have the distance, which is to measure 2 points in R2, right? And this formula is exactly the same as the absolute value. Okay, so a sequence of complex numbers, Zn, is said to be Cauchy if for any epsilon bigger than 0, there exists an n bigger than 0 such that the distance of the nth and mth guys in the sequence is smaller than epsilon for any n and m greater than n. So what this says is that for any precision epsilon bigger than 0, then I have a cutting point, which is big N, right? Such that if I go after the big N coordinate, the big N guy in the sequence, so after the nth, so the guy is getting closer and closer and closer in the sequence. So that is to say, Zm minus Zm, the distance, is smaller than epsilon for any n and m bigger than m. So why is Cauchy sequence important? So it will be showing up again in our study for differentiable, complex differentiable functions. But now, it will help us prove an important fact about the complex numbers. So the complex numbers C is complete. So that is to say, every Cauchy sequence has a limit in C. Okay. So why is this true? Let's consider a sequence of complex numbers. So let the n greater than or equal to 1 be a Cauchy sequence of complex numbers. Right? So we want to show that every Cauchy sequence has a limit in C. Right? So we start with any arbitrary Cauchy sequence, and then we want to find a limit for this sequence Zn in C. Right? So how do we do this? Well, first we observe that if we take the real part of Zn for each n, this is also a sequence. And this is a sequence of real numbers. This is a sequence of real numbers. And moreover, this sequence is also Cauchy. Right? So if you apply the definition for Cauchiness, it means the distance for any epsilon bigger than 0, and you can find a big N such that the distance between the nth and mth guys in the sequence getting smaller and smaller. So they are getting closer and closer. So this is also true for the real part of the members in the sequence, right? So if you take the real part of the members in the sequence, this is a Cauchy sequence of real numbers, right? So, and moreover, this is also true for the imaginary part. So on the other hand, imaginary part of Zn is also a Cauchy sequence of real numbers for the same reason. Right. So now we want to use the fact that the real number is complete. That is to say, every Cauchy sequence have a limit in R. Right. So therefore, I should say since R is complete, the real part of Zn, this sequence, has a limit in R, so which we call maybe alpha. Okay, and similarly, the imaginary part of Zn also has a limit in R, and we denote by beta, right? So then we claim that alpha plus I beta is the limit for the sequence Zn. And in particular, alpha plus I beta is a complex number, right? So we have shown that this sequence of complex numbers Zn has a limit in C, right? So therefore, Zn has a limit, i.e. this limit is alpha plus I beta in C. So this is to say, therefore, C is complete, because every Cauchy sequence has a limit in C, right? So this is basically the analog of the fact that the real numbers is complete, right? So the real number is complete, and today we also showed that the complex number is also complete. And complete basically means every Cauchy sequence has a limit in C. And the definition of Cauchy sequence and what does it mean for limit is given above, right? So yeah, so this is basically the limit. And we will see limit showing up again and again in our study for complex differentiable functions.